So, the way I'm going to start off here is we're going to go back and revisit some Physics 110 ideas as sort of a refresher, because reference frames are a big deal in relativity, and we want to make sure we properly understand what's going on in reference frames before we try to jump into more different ideas that are involve reference frames. A little more complicated, right? So, as you will probably, the topic of relativity was something that was pretty much exclusively developed by Albert Einstein. And in fact, there are a couple versions of relativity. One is called the special version of relativity, and the other one's called the general version of relativity. And general relativity is sort of the broader umbrella term for all aspects of relativity. And special relativity deals purely with constant motion problems. Which you'd think constant motion problems, oh, that's simple, right? Not so much. General relativity deals with acceleration, and in particular deals with gravity. And it is currently the best, well, it's currently the theory of gravity. I mean, theories being the best idea. However, there's been a lot of trends in astronomy, astrophysics basically, that are starting to question some of the ideas in general relativity. As you may or may not know, well, of course you got to know this, but back in the 1930s, around that time, was the detection of dark matter, or at least the idea that dark matter may exist. And it's been almost 100 years of searching for this elusive dark matter, and nothing's come up. And it has gotten a lot of physicists to sort of question the premise of dark matter. Maybe it's not matter. Maybe we have gravity not as understood as we thought. So it's very possible that general relativity gets either replaced or enhanced. Regardless, though, the ideas in relativity are definitely true. There may be, bigger things going on that we are not aware of, but what we're dealing with for the next 3 classes is what we call special relativity, constant motion stuff. All right, so here's the basics of relative motion in reference frames. So this should be very familiar to you, because again, Physics 110 material. So we have 2 different reference frames here, a S frame and an S prime frame. And terminology here is we typically talk about the S frame as being sort of a stationary frame, and the other frame moves relative to it. But of course, that's relative, because if you're in the S prime frame, you would say that the S frame is moving and you're stationary. So it really depends on who the observer is. But generally, we have a reference frame where we consider we're looking at one and we're stationary relative to it, and one moves. So we call that S and S prime. And there's coordinate systems that correspond to those, and they have coordinates that are either primed or not primed. Okay, and the idea, and you can do this 3-dimensionally, of course, but we're going to simplify everything to 1 dimension, because there isn't any kind of new physics when we go to 2 or 3 dimensions. It's just more math or something, not different concept. So this S prime frame is moving with the speed v relative to the S frame. Now, of course, this is relativity. So if you are in the S prime frame, you would speak of the S frame moving in the opposite direction with a negative v relative speed. And in this case here, these are what we call inertial reference frames. And inertial reference frames are where at least the first of Newton's laws are obeyed. All right, so question for you. There's a lot of questions today, actually. Which is an inertial reference frame? Which one of these is an inertial reference frame? A lot of you saying D. I don't like D. I don't like D personally. You're on the right track though. B then. It is B. So, when we talk about inertial reference frames, one very important concept in inertial reference frames is that no acceleration is occurring. There's an acceleration for part C, right? If a jet plane turns at a constant speed, well, there's a change in the velocity, right? Call that a centripetal acceleration. Yep. So C is not an inertial reference frame. And here's the problem with things that are non-inertial reference frames. If you have, say, for example, let's look at part A here, right? Part A, or option A. A jet plane during takeoff. Well, that's typically, that's acceleration that's happening there. And if we are standing on the ground and we look at that plane take off, when you see an acceleration, we can say there's a reason for that. That's what Newton's second law is. Newton's second law says there's a reason for that. It's due to thrust. It's a force, okay? And that causes the acceleration. If you're in the plane and you look at the ground, you'd give the appearance that the ground is accelerating in the opposite direction. Then you ask yourself, what force is responsible for the acceleration? Don't know. That means it's not an inertial reference frame. So the simple part of this is just no acceleration. And you can do, non-inertial reference frames. It's just not fun or relevant. Okay, so in our inertial reference frames, an event can occur. Say, for example, it's a firecracker that pops. Like last night when the Dodgers won. I was watching it on my computer here, and there was a little bit of time delay. So I'm sitting here, and all of a sudden I hear boom, 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 and I'm like, spoiler alert, people, with your fireworks. But anyway, it was only like 2 minutes off, but I was still like, I'm assuming the Dodgers won. But anyway, okay. So in the S prime frame, you can observe this event. It's located at some distance we call x prime from the axis here. And S would observe this as well with a coordinate x. And one of the things we want to be able to do with our reference frames is be able to talk to each other. And, these two reference frames may disagree about the position. Now, when I say disagree, I mean within their reference frames. For example, if we have, an origin or something, you say, oh, this took place 3 meters away. And the other person says, no, it took place 10 meters away. Okay, well, is there a way to reconcile those differences? Yeah, there is. They're called the Galilean transformations, which are these. So you'll need to know what the velocity of the frame is. And if you look back here, let's go back to this picture. So the relationship between x and x prime is the term vt. Vt represents a displacement between the two reference frames. So we think about a particular time that elapses between them, and say initially the origins coincide, and then the reference frame moves, and so the relationship between these two is there's a displacement of vt, and so that's what we have here. If I want to know what the position in the unprimed frames are, we add in the vt, otherwise we subtract it out. Okay. Now, same would go with velocities. If you observe an event take place, for example, you observe an object move in the S frame here, we have some object with a velocity vector that points up and to the right. We'll call that velocity u. what does people on the S prime frame see? Well, if you remember how relative motion works, there are components here, right? There is an x component that is along the direction of motion for the S prime frame. And so what happens is it gives the appearance that that object doesn't move as fast as it does in the S frame. So we actually subtract these velocities and we get, at least the components here, and we get a different looking velocity vector. It appears that the object goes more up than over to the right, but that's just due to the relative motion. So how would we do that? Well, we take all these equations here and we take their time derivatives. That's it. And if we take their time derivatives, that takes all these positions and it turns them into velocities. And so we get the velocity transformations equations. And the important thing here is just recognizing which to use plus or minus. So again, the U would be considered the stationary frame, the U prime is considered the moving frame, and V is an object that is observed in both reference frames. Okay. The scroll button is really confusing me here. If I scroll up, it goes backwards. But up seems forward to me. It's kind of messing with my head here. All right. So, now, there is a principle of relativity that has actually existed for hundreds of years, and it says something simple, that the laws of mechanics are the same in all inertial reference frames. So, if your two reference frames are inertial reference frames, meaning the reference frames are not accelerating, then there is a very simple way to talk about positions and velocities. And when you witness accelerations, those will be the same, okay? Because again, that would be some kind of change, right? So if I go back to this equation here, let's take another time derivative. If we take another time derivative, these velocities turn into accelerations, but V is a constant, so it's gone. And so there's no acceleration transformations. And so everybody agrees upon the same forces and the same accelerations. And everything is perfect with the world. Anybody in a reference frame can talk about any event, and if we disagree, we could exchange our transformation equations, and then we can give ourselves high fives. Say, yeah, we got it. We know what's going on here. So that's the classical way of things. All right, so let's go over a couple questions here. Ball 1 and ball 2 are about to collide. They have their velocities shown according to the S frame. We want to know what the velocities of these balls are in the S prime frame. The S prime frame is moving to the left here. So what would the velocity of ball 1 be in that frame? What do you think? Riley's correct, though. It is D. So, oops. Let's go back, though, and look at the velocity equation. So we want to know what the U prime is. U is a positive 2, and V is a negative 4. So that means 2 plus 4, giving us 6 for our velocity. Remember, these are vectors. I don't have them as vector notation because I've stated them as components. That's why the subscripts are there. But these are vectors. And so if you're going to use these equations, you got to make sure that you put an appropriate plus or minus sign indicating the direction that you've called plus or minus. Right? Okay. Now, there's a conceptual understanding as well. The concept is this. If the velocities are in opposite directions, now that could be moving toward or moving away, the velocities add. It looks like the balls are going faster, right? If the ball is heading toward you and you're going towards it, it's going to give the appearance that the ball goes faster, right? And the principle is if you move with the object, it's going to give the appearance that it goes slower. So there's the mathematical side of things, fine, but conceptually makes sense. So when you look at this, the objects are moving toward each other, it's going to give the appearance that it's faster, and the only option that's faster is D. Okay, great. All right. What about ball 2? What's the velocity of ball 2? C's good. C is good. Now, mathematically, right, you're doing u minus v. What's u? Minus 4. What's v? Minus 4. You're subtracting them, you get 0. Now, the conceptual principle is you're moving along with it. You're going the same speed as it. So it appears stationary to you because you're moving with it. All right. So, great. That was a review. But consider yourself to have now mastered Galilean relativity. All right, let's do mathematical example now. We jump to my worked out example here. Airplane is flying at a speed of 200 meters per second with respect to the ground. We got a sound wave approaching the plane from the front and a sound wave catching up from behind. Both waves travel at 340 meters per second relative to the ground. What is the speed of each wave relative to the plane? Okay, so when you attack these problems, you got to ask yourself 3 questions. What am I considering to be the S frame? What am I considering to be the S prime frame? And what is the object that the 2 reference frames are observing? Okay, well, relative to the ground, that's the S frame. The ground frame is the S is the ground frame. The moving frame is what the plane is going to see. Okay, the plane's going to see, and the object are the sound waves. So we got the ground as a reference frame, the plane as a reference frame, and both the ground and the plane are observing sound waves. There are 2 objects here, so we're going to solve 2 problems. Okay, there's sound wave 1, we'll deal with that first. Sound wave 2, we'll deal with that next. Okay, so we want to know what the speed of each plane is. We want to know the speed of each is relative to the plane. Now I wrote the equation down here, u equals u prime plus v. We want to know u prime, so I'm going to rearrange that. But let's go with sound wave 1 first. Sound wave 1 is approaching the plane. So I'm going to make the assumption the plane goes to the right here initially. Right, so initially my plane is going to be going to the right here, and that's what I'll call plane. That's not how you spell plane. Let's try that again. Got it. It's a little big. It's okay. And then we got a sound wave that approaches, right? So conceptually we know that it should appear like it's going a lot faster. So u is going to be 300. U is the velocity, right, of the object, 340, but minus 340, right? Because we say it's going to the left here. And then the reference frame is the plane, and that's 200. So we get a minus 540 here. So the sound wave appears as if it's moving faster. Great. Sound wave 2, it's catching up from behind. So now sound wave 2 is moving in the same direction. And so conceptually, this will not appear to go as fast. So the object, the sound wave, is going positive 340 now. The plane's still a negative 200. 200. But we're doing minus in the equation. And we get a 140 here. Okay? So these problems are about what's ground frame, what's moving frame, what are the object or objects. And you deal with one object at a time. Okay, any questions about this? I know it's review, but still. Okie dokie then. Let's push on. Now let's start looking at the modern view of these things. There are 2 postulates to the special theory of relativity. And the first of these postulates is the same, really, as the Galilean relativity. The laws of physics are the same in every inertial reference frame. Okay. The idea is that if you are moving at a constant speed, physics is not somehow different. Physics is the same. And in most cases, that makes a lot of sense. We see that's an example. If you're moving, at a constant 30 miles an hour in your car, gravity's not dramatically different, right? Nothing about gravity should be different, or electromagnetism. Sometimes it's not as obvious, and I know a lot of you have had Physics 120, so you're familiar with a lot of the ideas there, but electromagnetic induction is a good example of where seemingly different behavior is reconciled when you consider that you have inertial reference frames. So in the example here, we have a magnet that is pushed into a coil. Well, a change in magnetic flux is going to produce a current in the wire. Great. But if you instead take the coil and push it up towards the magnet, the exact same behavior occurs. Everything's fine because these are two different reference frames. And it's an inertial reference frame. So this is actually the exact same behavior. So nothing's really crazy there. Now, in electricity and magnetism, one of the things that you get to toward the end is you start looking at E&M waves, right? You start looking at EM waves, you start looking at the electric and magnetic fields. And one of the last things you do in Physics 120 is you start to look at the transformation equations, because you go all through electricity and magnetism. Then at the end of the class, they drop this, this conceptual bomb on you, and they say, by the way, electricity and magnetism are actually two perspectives of the same thing. That magnetic fields and electric fields are different manifestations of the exact same phenomenon. And so you learn about the transformation equations, where you can, if you ever move in reference frame, you can determine how the electric and magnetic fields look in those frames. And one of the things that comes out of that is that the constants that appear in the Biot-Savart law and in Coulomb's law show up as part of a wave equation, and the wave equation has a velocity to it that ends up equaling the speed of light. And that was a very important connection made, that light is electromagnetic disturbances, and they all propagate through space at the exact same value. That's C. So it's 1 over radical epsilon naught mu naught equals that speed of light, 3 times 10 to the 8. Now, those were laws. Those were a law of physics, right? And that speed is not something that light, just attains at times. It's a property of the light. It's part of physics. It is a law of physics. And when you tie that in to, that's sort of the second idea in relativity, is that it's the recognition that the speed of light is not the same thing as like the speed of a car or the speed of a plane. It's a fundamental property of the universe, really. And if the laws of physics are all the same in all inertial reference frames, then the speed of light is the same in all inertial reference frames. So, initially you hear that and you think, okay, well, that's fine, But then when you start to look at the details of it, something's fishy. Something's fishy when you start looking at the details of this. So, the point of this, the really profound idea, is to state that the velocity of light is a law of physics. Okay, and that it's the same in all inertial reference frames. That's what the second postulate is. Speed of light in the vacuum is the same in all inertial reference frames and is independent of the motion of the source. So we got these two observers here. well, Kathy's really the observer, and then Amy over here is shooting a laser beam and trying to destroy Kathy. She can't escape because Bill's going to do the same thing anyway. She should take a left, but whatever. That's not really the point of this. Anyway, these laser beams are gonna cut her in half here. But here's the beautiful thing about it: Bill's laser beam is not going to kill her first. She'll die at the exact same time, according to Einstein. Okay, so the idea is that Kathy is like really doesn't want to die here. Kathy's like, I'm not having this. I'm gonna somehow accelerate my bike at 90% the speed of light. Okay, so, and what we just learned in Galilean relativity is if we do that, well, Amy's beam should look like it's a lot slower, and Bill's beam should look like it's a lot faster. In fact, Kathy should be saying, in fact, I should put Galileo on here. Kathy shouldn't be on here. Galileo should be on here. So Galileo's on the bike, and Galileo is saying, yeah, Bill's shooting me with a laser at 1.9 C. And poor Amy back here, she's behind me, so this thing is only gonna go at 10% the speed of light. That's not true. That's not true. Galileo gets shot at the exact same time. Okay. And it doesn't matter how fast you move, those velocities don't change. Now that's where the counterintuitiveness comes from. And I mean, there's a couple reasons why this exists. One is because of both are due to a couple of assumptions that we thought were safe assumptions to make. But there's a history of making bad assumptions, right? I mean, the Greeks thought when they came up with their theories of how the solar system worked, they made a simple assumption that seemed obvious, that the Earth was stationary. And it took a very long time to make observations to prove otherwise. Well, same thing here. It may seem obvious that the Galilean transformation equations would apply to anything that moves. Turns out it does not. Also, there's some funky things going on with the rate at which time flows. We'll get into that near the end of this lecture here. But that's the important principle here. And in fact, this postulate is really the entire basis for special relativity. That's the only new physics that you are going to learn. So right now, you've learned one new idea, that the speed of light is the same in all inertial reference frames. And what we're going to do for the rest of this lecture and the next two lectures is nothing new. We're going to work on this premise, and then we're going to see how all the different parts of physics we've studied reconcile with this idea. So that's kind of neat in that way. It's not new physics. We're not going to learn any more new physics from here on out for the next, like I said, 2.5 lectures. We're going to work on this premise, and we're going to have to really think hard about what this means in different contexts. Okay. Well, this is nothing. Why is this even here? Why is this even here? Well, let's just say I already said all this stuff. All right.
Is it just explaining that, like, reference frames always use the speed of light? Or
no, it's not that they use the speed of light. If the idea, the idea is this: if we, all the stuff we talked about earlier here, if we have two reference frames and we're watching an object, that object will have different speeds depending on how things move. And the postulate is this: that's true, what I just said, except for light. If you're in different inertial reference frames, you will not disagree about the number that is the speed of light. You don't have to use any transformation equations. Doesn't matter how fast anybody moves. I'll go back to the meson example. Right here I just skipped over. The mesons are, these are something that's typically created in the atmosphere. It's something that can be created in the atmosphere, I should say. Cosmic rays can come down, collide with particles in the atmosphere, and then cosmic rays come down, and cosmic rays is just a fancy not a fancy, but a kind of a crude term for really high energy particles or light or something like that. But some really lightweight things like mesons, neutrinos, they travel at speeds that are close to the speed of light. Okay, so this meson is just hauling at 0.99975 c. What does the meson see when it sees light? Does it see light just kind of just travel along, going just a slightly bit faster? No, it doesn't. We see light go at 300,000 kilometers per second, and the meson sees 300,000 kilometers per second. That's it. What I'm asking you to do right now is to accept that as a fact. And what we're going to be doing for the rest of this lecture and for a lot of the next lecture is we're going to try to understand why that is the case. And I have bad news for you. At the end of this lecture, you're not going to feel satisfied. You're going to feel frustrated and confused.
Oof.
Well, let me tell you why. Because in 2 hours, I can't develop enough ideas to explain it to you. I'm going to show you a lot of different ways that this idea manifests itself. And then on Monday, we'll start putting mathematics behind it, and it will make a lot more sense. In fact, what I encourage you to do is after this lecture is over, jump into your textbook, and because the very next thing that we're going to do in our lecture starting on Monday is we're going to look at something called the time clock, time dilation, time clock, things like that. And it's a very simple experiment you can see where you can really visualize why, the speed of light has got to be the same in different different reference frames. So if you feel uncomfortable enough, jump in your textbook and look up let's say time clock. I meant light clock. Light clock. Oh my gosh, this book's gonna break my wrist. Let me just be really specific about what I'm talking about here. Jump in your textbook and section 37.3 goes over the light clock, and that puts the mathematics behind it. What we're doing today is just the first 2 sections of this chapter. Okay. So, let's keep going though. Okay. I don't got a lot of space here. Okay. There we go. All right, so question for you here, real basic stuff right now. Race car driver Sam is heading down the final straightaway, approaching the finish line at 100 meters per second. His fans at the finish line straight ahead are shouting. Great, good for them. Speed of sound on this very hot day is 350 meters per second. How fast are the sound waves? D. You bet it's D. It is D. Susie is heading down a straightaway, approaching the finish line at 1 times 10 to the 8 meters per second. Susie's pretty fast. Fans at the finish line straight ahead are shooting laser beams at her. That's rude. Speed of light is 3 times 10 to the 8 meters per second. How fast are the light waves approaching Susie's reference frame? Let her in the chat. Too slow. Too slow. C. You bet. Why? Because Einstein said so. Well, for now, that's the answer. Because Einstein said so. Let's think about it a bit more. Let's take a real simple example of observing an object moving in different reference frames. On the left here, we got, what was her name? Kathy? Kathy survived somehow. Kathy survived, and now she's just bolting, right? She's going past the tree and the light post, and she's getting out of here now. So, we're in the ground frame, and we're watching Kathy make a run for it. And we're going to talk about 2 events that take place. We're going to talk about when she crosses the tree. We're going to talk about when she crosses the light. Right? Well, there's a certain distance between those two objects. And based on their speed, we can talk about how much time elapses between the two events. So we say their velocity u is given by delta x over delta t. Great. If we're in the s prime frame, that means now in this particular case here, the s prime frame, we happen to be moving kind of along with Kathy here. Not as fast as her though, because she'd look stationary, but we were going a little bit slower. Remember, we're moving along in the same direction. So the idea is her speed's a little bit lower. And now these two objects here, the tree and the light post here, they're going to appear to be moving to the left. Now, because we're moving along with her, this delta x here is a little bit shorter. Okay, the distance between when the two events take place in this reference frame. Okay, in this reference frame. We're talking about events here. Events. When does she cross the tree? When does she cross the light post here? Okay, so when she gets to the light post, it's a shorter distance because, again, we are moving in that direction, so the light post is actually moving to the left there. And we would talk about her speed as being u prime, and that's different. The reason why it's different is because we measure the distance differently, because we're in a moving reference frame, delta x over delta t. Okay, great. That's fine, that's what we know. Now, what if we're not looking at Kathy now? What if we're looking at light? Replace the bicyclist with light. Now the postulate is u and u prime are the same. Okay, they're the same. Well, delta x and delta x prime, well, they're still different, but that would mean that u and u prime is different, right? So there's a problem here. There's a problem here. If we're saying, remember, you replace u with c. So we're saying that these two things are equal to each other. Okay? Now, let me bring up my... So, according to Galileo, right, u not equal to u prime. That's what Galileo says. But Einstein says, okay, well, c is equal to c prime. So that means delta x over delta t is equal to delta x prime over delta t. How could this be? This is not supposed to be Dr. Seuss riddle here, but the delta t's would cancel out, and then that would imply that the distances are the same. Well, they're clearly not the same, because the motion of the tree and the lamppost makes that shorter. So how do we reconcile this? All right, you see how you know how we reconcile it? Watch it. Watch this. Ready? You ready for this? I'm going to put a prime right here on the delta t. There we go. What does that mean? It means the time interval between these events are not the same. The time interval between these events are not the same. Down on the bottom here, we made that assumption, which is a good assumption to make. It's true that when she crosses the tree and she crosses the light post, the interval of time should be the same. Turns out that's not the case, though. When we deal with light, that's not the case. And the implication is time is flowing differently in the reference frames. So we need to start thinking differently about time. That's what we have to do at this point. We have to start thinking differently about time. Okay. Any questions about this? It's a little strange, but the only way you reconcile this, if you look at the postulate of the speed of lights are the same, is you got to throw a prime on that delta t. You got it. It's the only way this works. Throw a prime on the delta t.
So it's kind of like different bases for time then?
No, well, no, not that. I'm not sure exactly what you mean by that. Let me just sort of clarify what I mean here. the rate at which time flows is different.
Okay.
That's what it means. The rate at which time flows is different. Okay. So, well, okay, now we got to keep going. Now we have to start saying, okay, well, I'm not happy about this, but let's keep chugging along and try to reconcile this. So now we got to start looking at what events are and how we measure events. Okay? So this idea of events are very, very important. Events are how we're going to keep track of positions in time. So in the example again, I'm going to have a firecracker here. When the firecracker explodes, this is an example of an event. An event has, for every reference frame, a position in space-time, which are 4 coordinates, x, y, z, and t. Okay, so this firecracker exploding, according to the S frame, has a space-time coordinate x, y, z, and t when it occurs. And S prime has a different space-time coordinate. They would talk about different positions, but they would also talk about different times as well. And, you know, that, again, it may seem strange, but when you think about, oh yeah, well, yeah, they won't agree on the same positions. When I say they don't agree on the same positions, I mean like the numbers they would use. This is 3 meters away. This is 10 meters away. Yeah, those are clearly not the same because the origin is different, right? Well, that extends to time, even though it seems strange, but that does extend to time, and so that's why we blend these ideas together and we talk about space, time. If the speed of light is absolute in every reference frame, then you can blend these ideas together, space and time, into a single concept, which you call space-time. 4 coordinates, x, y, z, and t. Okay, so question for you now. What are we doing on time? Okay, we're going to take a break soon here before I really hurt your brain. Firecracker explodes high overhead. You notice a slight delay between seeing the flash and hearing the boom. At what time does the event firecracker explode occur? All right, so I got a couple examples here. All right, 2? Yeah, 2. Let's look at those. All right, so we got experimenter A in reference frame S, standing at the origin, looking in the positive x direction. Experimenter B stands at a position of x equals 900 meters, looking in the negative x direction. Firework explodes somewhere between them. Experimenter B sees the flash at 3 microseconds. Experimenter A sees the flash at 4 microseconds. What are the space-time coordinates of the explosion? All right, so we got 2 observers here. Nothing's even moving yet. Nothing's moving. I mean, the observers aren't moving yet. So I drew a little crude coordinate system here. Got observer A here. I'm going to place an origin at that location. For experimenter B, they're at 900, and just randomly I put the explosion here. Okay. So now, experimenter B sees this flash at 3 microseconds and A at 4. Clearly, B is closer to it. It took less time to reach B, right? So the way we're going to specify the distance here is I'm going to say that the explosion took place at some distance x relative to A. And then when we talk about B in reference frame S, the distance that B would say would be 900 minus x. So that would be this distance between the explosion and B here. Now, what I'm going to do here is we're going to state the speed of light in some weird units here just to make our math easier. So the speed of light is 3 times 10 to the 8 meters per second. Well, what would that be in meters per microseconds? Micro being 10 to the minus 6. Well, that would knock 6 off the index. 10 to the 8 goes down to 10 to the 2. So the speed of light is actually 300 meters per microsecond. Okay? So the time difference between these two events, is 1 microsecond. Because of that, the position, the change in position, the difference in the distance traveled would have to be 300. All right, 300. All right, so again here, if I've used the speed of light as 300 meters per microsecond, a 1 microsecond difference means a path length difference of 300 meters. And so then we can create this equation now, all right, that the distance from A, okay, is going to be equal to the distance of B plus this 300 meters. Okay, being the difference in the path lengths. So these are the two distances, but we know that A has a bigger distance by 300. So that's why the 300 is sitting here to represent that extra microsecond of travel that took place. You solve this equation for x, and we get that this must have taken place at 600 meters. Okay, great. If it took place at 600 meters, then the explosion apparently took place at 2 microseconds. So the time axis starts at 0 microseconds, and for whatever reason they decided to have their clock start at 0 microseconds, but the explosion didn't actually take place until 2 microseconds. So the distance to B is 300 meters. That took 1 microsecond. So it's 1 microsecond after the explosion, right? So 2 plus the 1 microseconds that. And then A's distance is 600. So that's 2 microseconds of time travel. And so the coordinates of this event, according to reference frame S, which is centered on experimenter A, is 600 meters is the position. Y and Z we'll just say is 0. And the time is 2 microseconds. 2 microseconds. So it's a kind of a simple problem, but you got to be very careful about how you specify positions, how you specify times and things like that. Okay, so if these two experimenters make their observations, they say, okay, this light this light flash happened at 3, and then once this happens at 4, they get together, they work out the speed of light and the relative distances that are involved, and they would both come to an agreement. Yes, this took place at 600 meters at 2 microseconds. Okay, so apparently 2 microseconds after wherever they started their clocks, for whatever reason that they did that. Okay, that's the space-time coordinates for that. Any questions about that? Okay, so when you do a problem like this, and obviously on your homework you're going to have problems like this, it's very important that you really draw things out. Draw things out, visualize it, create a coordinate system to organize yourselves. And depending on how the units are, I showed you a little trick here to do with the time. Now, do we have to do that? No. But you're going to be dealing with big numbers, and you're going to be fumbling over a lot of the mathematics. Changing the speed of light to this strange unit here just helps with the math. Because the concepts are already hard. You don't want the math to be hard too. If it doesn't have to be hard, All right. Let's get to the next example. All right. Experimenter in reference frame S stands at the origin, looking in the positive x direction. At 3 microseconds, she sees firecracker 1 explode at 600 meters. A short time later, at 5 microseconds, she sees firecracker 2 explode at 1200 meters. We want to know if these two explosions are simultaneous. And if they're not simultaneous, we'd like to know which one happened first. Now, she didn't see them happen at the same time. That's okay because they took place at different positions. We just need to reconcile whether those difference in positions do correspond to differences in time. Now, as you can see right off the bat, the answer is clearly yes. There's a 2 microsecond difference between them and a 600 meter difference in the distance. And we've already expressed our speed of light as 300 meters per microsecond. So clearly this does work. It is simultaneous, but let's just, go through it anyway. All right, so because we're 600 meters away, if we see it at 3 microseconds, it really took place at 1 microsecond. We see it at 3, the event actually occurred at 1 microsecond. So we would state the space-time coordinates as 600, 0, 0, 1. Great. Firecracker 2, if it's seen at 1200 seconds, right, that means it must have traveled for 4 microseconds. 12, what did I say? 12. If we see it at 1200 meters, right, then it must have traveled for 4 microseconds. And we take 4 microseconds off the 5, and the space-time coordinates are 1200, 0, 0, and 1 microsecond. Yeah! A Coke Zero. After that cup of coffee, forget it. I'm not sleeping tonight. Forget it. Sleeping's for chumps. Okay. So, now, if we're stating are these things simultaneous, there's a couple ways you can go about it. Like the thing I said initially, you can say, well, look at the time difference, look at the position difference that coincides with how the speed of light travels. Great. I like the way that I presented it, even though it may seem a little bit overkill, but it's a good idea to try to always put yourself in the idea of space-time coordinates. Even though in some problems it may seem like it's more work than needed. But let me tell you what's important about these. The problems won't always be this easy. And so you want to start to develop a consistent way to do your problems. And consistency is going to be more important than anything else, because if you stay consistent with the way you do your work, then later on when you get to things that are not as obvious or not as simple, you can apply the same principles and you can still get the correct answers. So that's why it may seem overkill to do this like this, but still, consistency is a big deal. It's a big deal. Okay. Any questions about these two problems here? A couple questions for you, conceptual questions now. Firecrackers A and B are 600 meters apart. Sam is standing halfway between them. Susie's standing 300 meters on the other side of A. So we got, A and B are 600 meters apart, and Sam's right in the middle, right? 300 on either side. And then on the other side of A, so 600 away from Sam, and then obviously 900 away from Firecracker B, is Susie. Sam sees 2 flashes from the 2 explosions at the exact same instant. According to Susie, Firecracker A explodes when relative to Firecracker B? Yeah, just B. Okay. Remember, according to Susie, look, Sam sees 2 flashes from 2 explosions at the exact same instant. So he is going to say they happened at the same time. When Susie talks, this is about when they occurred, not when you see them. Remember, big difference between when you observe an event and when it actually takes place. According to Susie, you could argue like, okay, well, you're being a little vague. Well, fine. But if anything, the purpose of this question is to communicate to you, once again, the importance between specifying observations and when events occur. Right. For Susie, she observed them at different times. But when she sits down with her pen and paper and works out the details here, she says, space-time coordinates, okay, of these 2 events, the t's are the same. Okay, the t's are the same. So You'll say it happens at the same time. All right, so again, you may look at this and say, well, you weren't really clear with what you mean. That's fine, but the point of the question was to again emphasize observe versus when it actually happened. All right, good job, Susie. Good job. So it's not a problem here. Let's get to that. Okay, you're standing 900 kilometers at 900 kilometers. No, you're not. You're standing at 9 kilometers. And your assistant is standing at 3 kilometers. We have a lightning bolt strike. We have an event at 0 kilometers. We have a second event. Lightning bolt 2 strikes at 12 kilometers. You see the flash from bolt 2 at 10 microseconds. You see the flash from bolt 1 at 50 microseconds. According to your assistant, were the lightning strikes simultaneous? If not, which occurred first? What was the time difference between the two? All right, so I drew a picture. It's very important to draw that picture. So I got a coordinate system here. You got lightning bolt hidden at 0, 3 kilometers over. We got my assistant. 9 kilometers over from the lightning strike, I got me. And then at 12, I got the second bolt here. All right, so we look at the times, we look at the distances, and we reconcile when they actually took place. Now, I'm only 3 kilometers away. Now, I got kilometers here. Okay, I'm not going to try to convert my units here. But instead of saying 300 meters per microsecond, let's just put in kilometers now, 0.3 kilometers per microsecond. Okay, or you can say, I don't want to deal with kilometers, just put in meters, and then I'll just stick with the 300. Whatever, fine, you can do that. Okay, so, what do you see? Well, let me see, hold on here. You're standing at that. You see, okay, yeah, you see 10 and 50. Okay, so, lightning bolt 2, it appears to you first. You observe it first. Now, 10 microseconds for a distance of 3 kilometers, right? That would correspond to, it's 3 kilometers, right? So 3 kilometers will correspond to 10 microseconds, it looks like. Okay. So, anyway, you would see that bolt 2 travels at 3 kilometers, which will take 10 microseconds according to the speed here. So, the space-time coordinates are 12, 0, 0, 0. Now, look what I did here. I put a 0 here because this is when I'm going to state my time axis to start. I have a space axis and I have a time axis, and I just thought it was easier to just say, okay, well, the first thing that happens is the lightning bolt strike. Let's call that t equals 0. So it happens at 0. You see it happen. You observe it at 10 microseconds. Great. Now, what about bolt 1? Bolt 1 has got to travel, 9 kilometers. That should take 30 microseconds. You don't see it at 30 microseconds. So you see it at 50 microseconds. So because you saw it at 50 microseconds, there's this 20 microsecond difference. So guess what? It didn't happen at 0. It must have happened at 20. And then it travels that 9 kilometers, which took 30 microseconds, and then boom, you see it at 50 microseconds. So the space-time coordinate for that event would be 0, 0, 0, 20 microseconds. So we would say, you would say, these are not simultaneous events. Okay? Based on the distance of that other light bolt, it came later than it would if it was simultaneous. So you're standing there at 0. Okay? 10 microseconds go by. Bam. You see the flash on the right-hand side. Another 10 microseconds go by, and the lightning bolt on the left-hand side hits. You don't see it yet, though. 30, 40, 50, boom, you see it. Okay, so specify the space-time coordinates here. These are not simultaneous events. They have a time interval of 20 microseconds. Now let's go to the assistant and see what the assistant has to say. Now, it's kind of like the assistant's kind of in the opposite position relative to you, where, you know, the lightning bolt on the right is now 9 away and then 3 on the other side. So at 9 kilometers, it should take 30 microseconds for the bolt to reach that person. So they see that bolt happen at 30 microseconds. Okay. And they know they're 9 kilometers away, so they would say, yeah, t equals 0, fine. And then bolt 1, though, has to travel just 3 kilometers. But now, remember, it went off at 20, right? And it only takes 10 microseconds to travel. So the assistant observes the lightning strikes at the same time. They observe the lightning strikes at the same time. But clearly, because they know there's a different distance involved, they are immediately going to say, well, there's no way these things are simultaneous. I saw them at the same time, but there's different distances. So now here's the key here. If you say there's a 20 microsecond difference in these events, the assistant has to say the same thing. What you observe can be different, fine. But ultimately, when you do your number crunching and you work out space-time coordinates, you're reconciling those differences, and you both will come up with the same space-time coordinates, everything as well. Okay, now remember, right now, nothing is moving here. No observers are moving yet. So events should be simultaneous. Nothing too strange here. Okay, nothing too strange. So everything makes sense here. Now, we're going through this stuff here because when things start to move, it gets a little weird. It's a little weird. So that's why we got to be really careful about specifying things when things are not moving before we start talking about things that are moving. Okay, so now what I'm going to describe here is a very famous little thought experiment that was actually devised by Einstein. And he wrote a book. He wrote a lot of books, but he wrote a book for basically the layman on the topic of relativity, to be able to basically explain relativity to somebody with a basic idea behind some physics, as a means to sort of communicate it to a wider audience. And so the thought experiment we're going to go through right now was ultimately something that Einstein cooked up. It doesn't go exactly this way. This is a slight variation of it, but it's basically the same idea. So let's go through this real carefully here. So now something's different. Now our observers are moving relative to each other, and we're going to consider events now. So there's a big difference here. So what we have set up here is we have Ryan, who's standing on the ground watching a railroad car go by. Can't say railroad. Ryan is watching a railroad. Can't do my R's, sorry. Railroad car go by. Okay, Peggy's on the railroad car. And don't worry about it says there's a light detector here. I'm not going to discuss the light detector stuff. If you read over the explanation, they have a thing about it. It's not important for this. But anyway, Ryan is watching this railroad car go by with Peggy standing in the middle, and there's 2 firecrackers on either side. Okay? And what's going to happen is, as soon as I gotta change this because I don't want to say railroad. I don't want to say railroad car too much. So as soon as the middle of the railroad car reaches Ryan, the firecrackers are going to go off. Boom. Okay. And they're going to leave very obvious traces that they went off because they'll, like, say they explode, they'll leave like burn marks on the ground. Right. Now, according to Ryan, the distance that the light from these two firecrackers, the distance that the light from the firecrackers have to travel are the same. And they went off at the same time, so the light signal is going to reach him. So when he specifies the space-time coordinates for this event, there'll be different positions, obviously, because one's on the left and one's on the right, but the t is going to be the same for both. So whatever that, so, we'll call that t equals 0. And then, so that's the space-time coordinate. So there's this one and this one, the space-time coordinate for time is 0. And then he observes some later time correspond to how far, the light had to travel. Great. Simple enough. Okay, so that's what Ryan says. And here are the events. Here are the events according to Ryan. So, the railroad car gets right, the middle gets right in front of Ryan. Boom, the explosions happen. And now, the light is traveling, right, towards Ryan, towards Peggy, but the railroad car is moving to the right. So, according to what Ryan's saying is, oh yeah, Peggy, this thing's going to hit Peggy first, and then the other one's going to hit Peggy sometime later here. But what happens is the distance that the light travels in the x direction is going to be the same. So by the time he sees the event, the train's going to move by a little bit. Peggy won't be in front of him anymore, but he will report the same time and the same distance traveled. Okay, that's perfectly fine. That makes a lot of sense. Okay. And he would actually say here, he would say, oh yeah, Peggy should see that, that should observe the one on the right happen first and the one on the left happen a little bit later. Because she's moving towards that one, right? Okay. Now, what does Peggy see now? Peggy does not see. Not only does she not see, but she actually will report that the events are not simultaneous. She will say that the firecracker on the right will explode first, and the firecracker on the left explodes later. Okay, so let's look at it from her reference frame. Firecracker explodes, the right wave reaches Peggy first, right? And then the next one explodes, travels a short distance, and then she sees when they reach Ryan. And she says, yeah, okay, I agree that he says they're simultaneous. But the only way for this to work in her reference frame, because she's moving, is if the one on the right actually explodes at the first, to begin with, at first. Because she's moving towards it, remember, the speed of light is the same in all reference frames here, and that's where the paradox sort of comes from here. To reconcile this, the one on the right has to explode first, the one on the left has to explode later. She's moving toward that ray there, but that light ray is going at the speed of light, and the other one's going at the speed of light. So in order for them to meet up with Ryan when they're supposed to, the one on the left is going to have to explode later. I mean, you could argue, you could just say this. I mean, the way we're actually going to do this, because what's going to happen is on Monday, we're going to look at the light clock. We're going to start to put some mathematics behind it, and then we're going to revisit this problem and put the numbers behind it. Because right now I'm telling you, you got to believe it. You got to accept it. And you say, I don't want to accept it. It doesn't make any sense. It seems foolish. And I say, okay, wait till Monday. And we'll put numbers behind it, and you'll see how the numbers work out here. But anyway, in order for Peggy to see these light rays hit Ryan at the same time, the one on the right has to explode first. It has a longer distance to travel compared to the other one because it's moving towards Ryan. The other one's moving away from Ryan. So this whole idea is called the relativity of simultaneity. And it's a simple idea that in moving reference frames, events that are simultaneous in one frame may not be simultaneous in the other frame. And this ultimately comes from the idea that the speed of light has to be the same in all reference frames. Remember back earlier when I talked about the person on the bicycle, in order to reconcile the fact that the speed of light is the same, we had to say time is flowing differently, and this is another manifestation of that idea that time has to flow differently. But it's the only way to make Ryan see the flashes at the same time. Okay, so we're going to turn this around in a minute here, though. Well, I guess we're going to do that right now. All right, so we're going to turn this around now. Okay, so I ask you a couple questions in order to turn this around. Because, this is all relativity here, right? So we're talking about Ryan here. Ryan sees things simultaneously, and then Peggy, in order for Peggy to witness that the light rays do hit Ryan at the same time, the only way that makes sense is if B happens first. So let's flip it around. So let's question first. Peggy is standing at the center of a railroad car as Ryan passes. As it passes Ryan, okay, that's the same premise. Firecrackers A and B explode. A short time later, flashes from the explosion reach Peggy at the same instant. So this is different now. We're flipping it around. Before Ryan saw them at the same time and they were the same distance apart, those events were simultaneous. Now we're flipping it around. We're focusing on Peggy now, and there's a different event taking place here. Different events taking place. The explosions are equal distance from Peggy, and she witnesses the explosions at the same time. Okay, so these are different events. We're flipping it around here. Okay, in Peggy's reference frame, firecracker A explodes when compared to firecracker B. Okay, the answer is B. Because the firecrackers are the same distance from Peggy. She sees them at the same time. Therefore, the events are simultaneous to her. Okay, in the previous example, though, the firecrackers are the same distance, but she saw B first. She sees A later, indicating that B must have happened earlier. That's the only way it can happen if they're both going to reach Ryan. Follow-up question now. What does Ryan say now? Okay, we know what Peggy sees. Simultaneous fireworks going off. She sees that. She observes it. She works it out. Okay, simultaneous events. What does Ryan see? How does this work for Ryan? How can Ryan reconcile this? What will Ryan see? This is like the climax of the whole lecture here. You get this right, congratulations. If you got it wrong, you've wasted the last 2 hours of your life. Don't get it wrong. I'm just joking. Don't worry about that. But no. Remember this, right? In the previous example, the distance that A had the trouble was kind of shorter for him. Well, I mean, according to Peggy, right? According to Peggy. Oh my goodness! I see all A's. Son of a gun! Congrats! Congrats! It had to happen before. Because Ryan has had. What does Ryan have to see? Ryan has to see that the two light rays reach Peggy at the same time, because that's what she says happens. But the only way that can occur is that A has to go earlier, because it's got to cover more ground, right? B is going towards Peggy. Sorry, B and Peggy are going toward each other. Peggy and A are going. Peggy's going this way, and A has to catch up to Peggy here. So the only way this works is if A has to go off before B does. A's got more ground to cover. So what Ryan says is, A went off first, traveled for a bit, then B went off, and then bam, they met at Peggy. So Ryan has to agree that the flashes reach Peggy simultaneously because their arrivals could be measured with... don't worry about the detector thing. I don't like the detector thing. Anyway, so, good. Great. By the way, I'm going to hit my video here. I want to say a few things before we actually finish up. Let me just kick my video here and